Next segment, the news. If you want to look at your screen,
I'm good. I'm going to conserve battery life by keeping the screen time at 0.
okay. Well, the Large Hadron Collider turned back on for the first time in 3 years.
Goes off.
Yeah, it hasn't been. They've been upgrading it.
Oh,
I figured you knew this.
no. I'm sorry. I didn't follow it.
Okay. Anyways, uh, they turned it on. It broke a world record. I mean, it's not much of a world record. I mean, I think it held the previous world record, and since it's the only one that was large enough to do that world record beforehand, and it was being upgraded, and was the only one under construction to make more powerful beams. It it it's kind of stupid, but anyways, the record, the beams were each 6.8 tera electron volts per beam. Very exciting. Now, if I'm not mistaken, from what I've heard from like Dr. Becky and other things, or me, these higher energy beams are good because that gives us a higher probability of getting things like Higgs and other other particles. Correct?
Sorry, I was looking at some. Say it again.
So that these more energetic beams give us a higher probability of finding particles like the Higgs. Right.
Uh, Maybe. I don't know much about it.
Oh, I thought you knew a little bit about particle physics.
I know a little bit, but I guess what I can say is that
And
basically, with more energy, you hope to break the particles into smaller and smaller fragments. Eventually, they're elementary entities that make them up. And I guess there becomes a point where you reach the fundamental entities where just driving more energy into it accomplish a higher probability. I don't know, because it seems to me if you've already crossed the threshold of what it takes to break it into its fundamental entity, I don't know what purpose putting more energy into it does, other than the fact that we are in the dark on whether or not there truly are fundamental entities. You know,
mm.
I mean, we're fairly certain that there are, particles that cannot be broken up further. Uh, Likewise, things like the Higgs.
That was wrong.
What's up?
That was the wrong Higgs.
Yeah, things like the Higgs. I don't know exactly how their role plays in the probability game of what you get when you break something up. But
So what I thought was interesting with this new round of research is they're looking for, I don't remember what particles they're looking for now, but part of it was to look for dark matter now.
Okay.
Which is interesting. I'm not sure how they plan to use a particle accelerator to look for dark matter,
Yeah.
but fair enough. Uh, there was a Dr. Becky video actually you should watch. It's very interesting. She talks about, in it. She talks about how do we know that big G is constant. Because she said of all the constants in nature that we've measured, it is the one we have the least precise measurements of. And we've only really been able to measure it here on Earth. And if big G is different, then then that could in other places that could explain these galaxies spinning at rates that just don't make sense.
Yeah. Yeah, what's crazy is that big G, its value hasn't really changed much. The first experiment done by Cavendish
Yeah, it was
to find big G
stupidly precise.
was within 1%. It might have even been slightly less than 1% of what the current accepted value is. And it's because it is just that small, and the techniques haven't improved the precision that much because you're measuring something so small.
Mm-hmm.
Magnitude of 10 to the minus 11. Very small.
Mm-hmm.
And so you have to be very, very precise in what you do to get better measurements. However, the thing is that since it's so small and there's so much air in everything you do, you can't improve much. Mm-hmm. We haven't been able to improve much more.
My thing is, I love. Wasn't his experiment literally just two giant? Wasn't his experiment like he had a giant steel or lead ball, then had a small steel or lead ball, and then measured basically that force of attraction between them?
He measured the distance. So basically, he had two lead balls, giant lead balls, and then two more smaller ones. Mm-hmm. And they're on a torsion rope that would spin. This is how I did it, because my junior year we performed the experiment, and it was more or less how he did it too. Mm-hmm. However, we had the added advantage of lasers.
Oh.
He had to use sunlight. But basically what it was there were mirrors attached to these on the rods. Mm-hmm. And as light reflects off of one and onto the other, it would reflect off onto the wall. And so you would see two laser dots on the wall. Mm-hmm. And they would oscillate amongst each other. And their oscillation was dependent upon the force of attraction between them. Okay. And we recorded the data of how long it took for an oscillation. Mm-hmm. If I am remembering this correctly, there is a formula that relates how much the oscillation slows down over time to the gravitational attraction.
Okay.
And actually, his original measurement was not to measure big G. His original experiment was to weigh the Earth. He wanted to know what the mass of the Earth was. Mm-hmm. he knew the volume of the Earth. It was from the Greeks. The Stratosthenes already had calculated what the radius of the Earth was, but he did not know the density.
Mm-hmm.
And so in order to calculate the density, he had to perform this experiment, which gave him big G and the rest of the data necessary to calculate the mass of the Earth.
Mm-hmm.
And actually, side note, Newton, about 70 years before this experiment, because this experiment was performed after Newton died.
Mm-hmm.
Well, Newton had wanted to calculate and make predictions with his gravitational formula. And the problem was he didn't know big G.
Mm-hmm.
And so he guessed big G. He made an approximation that the density of the Earth, based upon dirt, rocks, water, and the fact that the core, things under pressure compress, he made an estimate that the density of Earth is more or less 6 kilograms per meter cubed.
Mm-hmm.
That was his guess. If you know what the actual value is, then you would be just baffled by the fact that he just pulled that number, because that number is more or less the right answer. It is what is known as Newton's lucky guess, because he guessed the density of the Earth to such a close value that his big G value was more or less correct. And so all of his calculations done on planets and masses and things
Mm-hmm.
were all done from the big G value. He estimated it to be from the density of the Earth that he guessed.
Well, I always
Called Newton's lucky guess, yeah.
Yeah, I always found it interesting was that they were doing so without Big G. I always found it interesting. I'm like, how the heck was Newton predicting the paths and movement of Jupiter's moons?
Because he guessed the value.
Right, and I had a suspicion like he had to have just guessed, because
Yeah.
even with Cavendish's experiment, we don't know what without putting something into orbit around Earth, which is, in my opinion, probably the best way to freaking measure, the speed necessary to, without putting something in orbit around Earth, it's hard to, know for certain these are what your experiments are.
Yeah.
These are what these constants are supposed to be, because once you put something in orbit, then okay, I know its mass, I know its speed, and I know its distance from me. Therefore, I can calculate what the mass of the Earth is. But, they couldn't put something into orbit, and they always told me to use Jupiter's moons. I'm like, but we don't know the mass of Jupiter's moons. The only way we could know is if you guessed.
Because the thing is, we knew the force of gravity. We knew the acceleration due to the force of gravity.
Oh, yeah, we've known that forever.
We had obviously, Newton had a different value because the meter was not invented yet. The meter was not invented till 1798. And so, but using the units at his time, we can estimate that he estimated it to be 9.8, which is more or less correct, And so, but the thing is that knowing that value, the acceleration due to the force of gravity, you still have two unknowns in the equation. F equals G times M divided by R squared. And so you still have two unknowns. You still have G and M.
Yeah.
So you could make G whatever you want and make M the new value to get the right answer for the force of gravity. G and M can be whatever the heck they want. And for most cases, and for cases on Earth, it really doesn't matter because you know the value of that they are combined. However, the problem is that you cannot make predictions about other planets because you don't know M. And you can't find M without G. So you need to know G, which is why he guessed G, so he could make predictions.
What a guy.
And there had to have been more thought. I really want to know his thought pattern on 6, the number 6. He must have had some empirical data that he was pulling from, because just simply knowing the density of rocks and dirt, I mean, there must be another formula to estimate compression and pressure to the center of the core.
I mean,
Because not only
he
that-
also
not
made
only
calculus on a bet.
But not only that, he didn't even know what the core was made out of.
True. That
The
is
core is
kind of
not
crazy.
made of dirt and rocks. It's made of iron and nickel.
Right. Which makes you wonder, like, how the... Were his equations... Were his
Yeah,
equations off?
Yeah, I mean the maybe they did know though that the idea of magnetism and compasses had been known since ancient times. Except I've never actually bothered to look it up to see if they had any predictions on how it worked. Because he could have also then predicted,
Max...
obviously,
Well, they
there's
had...
3 choices. There's literally 3 choices: iron, nickel, and cobalt, that are at the center of the core, and it happens to be 2 of them. And they're all pretty close to the same density as well.
I just watched a video where they talked about that, actually. Up until Maxwell's equations, they had no idea. They had a guess, but it wasn't a very good guess. They were pretty rough. Up until Maxwell, they didn't have a freaking clue.
Yeah.
I don't remember what video it was or how the heck it came about. Why Maxwell ended up being like, yeah, this is it. I don't know. Oh, yeah. But without Maxwell, they had... Their guess was rough. It hadn't really changed since the Greeks. It was rough. Anyways, I was gonna. We have one more article, but we're trying to keep this short. It just talks about NASA's plans to explore more planets, which I've talked to you about with their Uranus. Wait, these are old. These are all the current missions. What? Okay. Whatever. Doesn't matter. Point is,